Stains and staining solutions. Biological stains are color-ranging agents used to enhance contrast in microscopic tissue examination. Type of dyes. Natural dyes from sources like cochineal, logwood, and plant extracts. Synthetic dyes such as aniline or coal tar dyes. Natural dyes sourced from plants and animals originally used in textile dyeing. Common examples used in histology: hematoxyzilline, cochineal dyes, and their derivatives, orcine, and saffron. Hematoxylin, source derived from the heartwood of Hematoxylum campesianum, a tree native to Mexico. Significance: highly valued for nuclear and chromatin staining. Produces permanent stains with strong contrast. Usage is works well with almost all fixatives, commonly used with mordants to enhance staining results. Ripening of hematoxylin. Hematoxylin is not a true dye. It must be oxidized into hematine, the actual staining agent. Ripening methods. Natural ripening exposed to air and sunlight for 3 to 4 months. Artificial ripening uses chemical oxidizers like hydrogen peroxide, mercuric oxide, potassium permanganate, sodium perborate, sodium iodate, and the important is the correct amount of oxidizer is crucial of ripening reduces stain quality. Mordants in hematoxylin staining. Mordants are chemical agents that help the dye bind securely to tissue, forming a stable dye tissue complex. Common mordants used with hematoxylin include alum or potassium aluminum sulfate, iron salt, example is ferric chloride, chromium salts, and copper salts. Types of hematoxylin stains. Number 1. Alum hematoxylin, used in progressive staining, often counterstained with eosine, Congo red, or safranin. Examples: Ehrlich hematoxylin, ripened with sodium iodate, and Harris hematoxylin, ripened with mercuric chloride. Number 2. Iron hematoxylin, used in regressive or differential staining, requires acid alcohol for differentiation. Example: Weigert's iron hematoxylin uses ferric chloride. And number 3. Copper hematoxylin, specialized stain used for studying spermatogenesis. Hematoxylin and eosine staining. Purpose: the most widely used protein stain in histology. Function: hematoxylin stains nuclei and acidic structures blue. Eosine stains the cytoplasm, collagen, and extracellular components in shades of pink to red. Eosine. Characteristics: strongly absorbed by red blood cells, making them appear bright red-orange. Produces different pink tones in muscle, collagen, and other tissues. And note on quality: manual staining highlights subtle color differences better. Automated system may miss these finds and use eosinophilic details. Cochineal dyes. Source: extracted from the female cochineal insect or Coccus cacti. Treated with alum to produce the dye called carmine. Applications: a strong stain for chromatin and nuclei, especially useful for fresh tissue samples and smear preparations. Specialized combinations: picrocarmine or carmine plus picric acid, widely used in neuropathology. Best carmine, carmine plus aluminum chloride, used to demonstrate glycogen in tissues. Orcine. Source: a natural vegetable dye extracted from lichens. Lichens are originally colorless but turn blue or violet when treated with ammonia and exposed to air. Properties: acts as a weak acid and is soluble in alkalis, mainly used to stain elastic fibers in tissues. Or related dye. Litmus, also derived from lichens but treated differently. Not used for cytological staining due to poor staining ability. Commonly used as a pH indicator in synthetic dyes. Aniline or coal tar dyes. Originally made from coal tar derivatives. Chemically derived from benzene or C6H6 compounds. These dyes are collectively called aniline dyes. Key chemical components of dyes. Chromophores, atomic groups responsible for producing visible color, found in chromogens, which are not true dyes because their color isn't permanent. oxochromes added to chromogens to help them retain color in tissues, enable electrolytic dissociation and salt formation with tissue components. True dyes consists of chromophore plus oxochrome attached to a benzene ring. Chromophore provides the color, oxochrome gives the dye its ability to bind the tissues. Classification of synthetic dyes, acid dyes. The active coloring part comes from the acid component of the dye. Example is acid fuchsin, a sodium salt of sulfonate of rosandolene. Picric acid unique because it can fix, differentiate, and stain tissues. Uses of picric acid act as a counterstain to basic cytoplasmic stains and part of Van Giosson's stains for connective tissue and used as a counterstain with crystal violet, common in fungi studies. Also functions as a fixative, decalcifier, and tissue softener. Tissue affinity to acid dyes. Basic cell structures like collagen and eosinophilic granules are acidophilic and stain well with acid dyes. Tissues fixed with trichloroacetic acid, picric acid, or chromium show increased uptake of acid dyes. Basic dyes. The active coloring part is in the basic component which binds to acid radicals like sulfuric, acetic, or hydrochloric acid. Example, methylene blue acts as both a dye and an indicator. It is widely used for bacterial staining in microbiology. Tissue affinity. Acidic cell structures such as chromatin, mucus, and cartilage matrix are basophilic and take up basic dyes. Tissues fixed with mercuric chloride or formaldehyde tends to absorb basic dyes better. Neutral dyes formed by mixing aqueous solutions of acid and basic dyes can stain both cytoplasm and nucleus simultaneously with different colors. Properties: form large molecular complexes, mostly insoluble or slightly soluble in water but soluble in alcohol. Tissue affinity. Tissues fixed with ethyl alcohol or acetic acid absorb both acid and basic dyes well. Example, Romanowski dyes used in hematology. Gemsa stain, Irishman stains for leukocyte differentiation.
Now we will be discussing common staining solutions in histopathology. First is the hematoxylin and eosin, which is the H&E stain. That is a routine staining for most histopathological examination. We use hematoxylin to highlight nuclei as blue or purple stain, and cytoplasm using eosin to have a pink or red stain. The advantage of H&E is simple, inexpensive, and widely available, and it provides good overall tissue morphology, while it has also a limitation because it may not differentiate all tissue components equally because some of the structure may be masked by others. Second is the periodic acid shift or PAS. It detects carbohydrates and glycoprotein like glycogen, mucus, and fungi. It also stains structures with the use of magenta or pink color. The advantage of PAS or periodic acid shift is it is a highly specific for carbohydrate, which is a useful in diagnosing certain diseases like glycogen storage disease. Also, it has limitation or disadvantage because it can be less sensitive than other methods and it requires careful technique. The third one is gram stain. Gram stain differentiates bacteria into gram positive and gram negative based on the cell wall composition. It is also crucial in infectious disease diagnosis. The advantage of gram staining is rapid, simple, and widely available. It also provides crucial information about bacterial infection. And the disadvantage of this is not applicable to all microorganisms, and it also requires proper technique for accurate results. Hematoxylin and eosin staining, which is the gold standard for routine histologic examination that provides a comprehensive overview of the tissue morphology. Also, the stain of H&E differentiates between acidic and basic components of all of the cell and the tissues. While the eosin is the acidic dye that is attracted to basic structure, which is acidophilic, that stains the cytoplasm pink or red. It also contributes to overall tissue contrast and visualization. The advantage of H&E is widely available and inexpensive, simple, and relatively quick staining procedure. It also provides excellent visualization of overall tissue architecture, and it allows for differentiation of key cellular components. On the other hand, it also has a limitation, like what I've said earlier, that it may not differentiate all tissue components effectively because some of the structures might be masked by others, and also it is not ideal for visualizing specific molecules or microorganisms. Aluminum hematoxylin staining techniques are used for both progressive and regressive staining method. It uses mordants like aluminum salts, which are crucial for the staining process. The resulting color depends on the mordant used and the pH of the solution. The progressive staining, the tissues are stained for a predetermined time to achieve the desired intensity. The nuclei are stained, leaving the background relatively unstained, and the stained sections can be counter-stained with eosin, Congo red, or safranin. While the regressive staining, the sections are overstained, and the excess stain is removed through differentiation in acid alcohol. Also, bluing is a crucial step to neutralize the acid and restore the blue color. The bluing process, bluing neutralizes the acid and frees the alcohol group or OH group. This forms an insoluble blue aluminum hematine tissue lake. The methods for bluing include using tap water, ammonia water, lithium carbonate, or Scott's tap water substitute, and each has different requirements. Factors that affecting bluing process are water temperature because it significantly impacts the speed of bluing. When we use very cold water, it slows the process, while when we use a warm water, it accelerates it. Using very cold water can also lead to pink artifact discoloration. Next is the Ehrlich hematoxylin staining solution, which is a generally used for regressive staining because the deperoxidation is done with 1% hydrochloric acid in 70% alcohol. Ehrlich hematoxylin selectively stains nuclei, and it is suitable for tissues that have undergone acid decalcification. It is also particularly useful for tissues that have become acidic during the process or storage in formalin. It has also the ripening process, which the natural ripening takes about 2 months, and the solution's color changes from purplish to deep red during the ripening. The pungent odor of acetic acid is replaced by the pleasant aroma. We also use stabilizer, which is the glycerin that acts as stabilizer for retarding evaporation. We also adding sodium iodate to hasten the ripening, but it shortens the shelf life. The limitation of earlich hematoxylin is not ideal for frozen sections because the typical staining time of this is 15 to 40 minutes. Harris hematoxylin staining solution is a example of good regressive stain that is widely used for routine nuclear staining, exfoliative cytology, and staining sex chromosome. The usual staining time of this is around 5 to 20 minutes depending on the factors like the batch and the age of the stain, also the tissue. The best results are also obtained when the solution is made every 2 or 3 months. The ripening process of this is that the solution should assume a dark purple color when ripened by mercuric oxide by adding 4% glacial acetic acid that can improve nuclear staining. The Harris hematoxylin is stable for about a long time like 6 months, and evaporation of alcohol is also a concern because adding ethyl alcohol can help prevent mold growth, and the precipitate should be filtered off before usage. Coles hematoxylin is an alum hematoxylin solution which is recommended for routine purposes, especially used in sequence with celestine blue. It is artificially ripened with an alcoholic iodine solution that is ready for immediate use but may need filtering after storage. The staining time of Coles hematoxylin is around 10 minutes. Meyer's hematoxylin is an alum hematoxylin which is a chemically ripened with sodium iodate that can be used as regressive or progressive stain. It also used as a nuclear counter stain to demonstrate the cytoplasmic glycogen, and it is also used in celestine blue hemalume method of nuclear staining. It also has a shelf life for 3 to 6 months. Iron hematoxylin staining is used only for differential or regressive staining because the acid alcohol is employed as differentiating agent, and it also has a two main iron hematoxylin solutions which are Weigert's and Heidenhaus. They also differ in the mordant use like ferric ammonium chloride versus ferric ammonium sulfate. They produce a intense blue-black color. Mordant and staining mechanism of this is that the ferric salt acts as mordant because they bind to the tissue, enhancing the hematoxylin binding and resulting in a more intense stain. The tissues are fixed in virtually all fixatives that can be stained. Tissues also stored in alcohol for years that will still stain, and the extent of the differentiation determines the final color, which is the blackish or grayish color, which is a useful for photomicrography. The optimal iron salt concentration and stability is the correct amount of iron salt is 0.5 gram metallic iron per 1 gram of hematoxylin because the correct amount are crucial. The stain becomes more selective for nuclei if acid or an excess ferric salt is added. Ferric salt can also hasten the ripening, and the premix stains are not very stable because the insoluble lake gradually precipitates out. Regod's hematoxylin is a simple and permanent method for staining mitochondria by light microscopy. The sections are fixed in formalin, and then we use a mordant like dichromate. After staining, the slides are differentiated to remove hematoxylin from cytoplasmic components, and the results may be uneven. Some around may be overstained, some are unstained or understained. We also have Weigert's hematoxylin staining solution, which is a standard iron hematoxylin stain solution in laboratories. It is also especially recommended for demonstrating muscle fibers and connective tissue, particularly useful when the preceding stain contains acid like banjeson, because the acid in banjeson decolorizes the stain with alum hematoxylin. The staining property and stability is the working solution, which is a deep black mixture that remains active for 1 to 2 days. The color also changes from deep blue black to violet, purple or brown, and yellowish brown as it becomes less stable. The discarded solution have turned brown. Heidenhain's hematoxylin staining solution are popular cytological stain, especially for studying mitosis, that can be used after almost any fixative. It also stains chromatin material like nuclear network and chromosome, which is color blue-black. How Heidenhain's hematoxylin work: we use ferric ammonium sulfate as both oxidant and mordant and differentiating fluid. Mordant differentiator is used separately during staining, and it is recommended for regressive staining. Remember that all components are black or dark gray black after staining. Progressive staining is also possible by moving sections through diluted iron alum solution, because the differentiation rates can be controlled. We uses Heidenhain's hematoxylin for the demonstration of both nuclear and cytoplasmic inclusions like chromatin, chromosome, nucleoli, centrosome, and mitochondria. The muscle striations and myelin are also well stained using this solution. Phosphotungstic acid hematoxylin staining are many variations of the original Mallory phosphotungstic acid hematoxylin exists, because it combines hematoxylin with phosphotungstic acid that acts as a mordant. It also has a natural ripening with light and air that takes several months, and the immediate ripening is possible using potassium permanganate. The ripening and staining characteristic of PTAH is that it takes several weeks or months for natural ripening, while for immediate ripening using potassium permanganate yields a solution with a shorter lifespan. The staining activity ranges from reddish brown to purple, and the stain is not reliable for all tissue. PTAH stains nuclei, fibrin, and muscle striation that stain reddish brown to purple. Myofibrils are colored blue. Collagen, bone, and cartilage stain orange, red, or brownish. Staining is usually progressive because the microscopic examination is also recommended every hour, and the 95% alcohol removes the red component. When to use PTAH is that for suitable for paraffin, celluloid, and frozen section that has a typical staining time around 12 to 24 hours. Eosin staining is one of the most valuable stain for differentially staining connective tissues and cytoplasm. The red general cytoplasmic stain, often used in conjunction with hematoxylin, to give an orange-red color in histopathology. It also can be used after any fixative and commonly used as a counter stain in hematoxylin. We also have two types of eosin, the eosin Y and the eosin B. Eosin Y, or the yellowish eosin, are most commonly used and readily soluble in water and alcoholic solution. It shows green-yellow fluorescence, especially in alcoholic medium, and aqueous stain is used as a 1% solution for 15 seconds to 3 minutes, while the eosin B, or eosin bluish or imperial red, has a faint bluish cast, which is interchangeable with eosin Y, eosin S, and eosin B, Eosin B are now rarely used. Eosin fluoxin B solution combines eosin Y and fluoxin B that produces a cytoplasmic stain that demonstrates various tissue components more dramatically.
While hematoxylin and eosin or the H&E stain remain the cornerstone of routine tissue staining, numerous specialized stains collectively referred to as other stains are used to highlight specific cellular and tissue components. These stains are indispensable in differentiating connective tissue, detecting microorganisms, highlighting cellular structures, and revealing biochemical components like DNA, calcium, and mucopolysaccharide. So first is the acid fuchsin picric acid or the Van Gisson stain. The Van Gisson stain is used primarily for demonstrating connective tissue, particularly collagen fibers which are stained red, while muscle fibers and cytoplasm appear yellow, and the formula consists of a 100 ml of saturated aqueous solution of picric acid that is combined with 5 ml of 1% acid fuchsin, and this solution weakens over time, so it should be refreshed by adding a few drops of fresh acid fuchsin. Acid fuchsin or Masson stain. Acid fuchsin in the Masson's trichome stain is utilized to stain a variety of tissue structures including collagen, smooth muscle, cytoplasm, and mitochondria. It is a key stain in protocols like Masson's and Mallory's trichome, and also in Van Gisson's where it gives a red color to collagen fibers. The formula consists of 1 gram of acid fuchsin, 1 ml of glacial acetic acid, and distilled water to make 100 ml. Third is the picrofuchsin solution. The picrofuchsin is used in the Van Gisson stain and provides distinct color separation for different tissues. Collagen is stained red, and other tissues like muscle and cytoplasm are yellow. The solution is made by mixing 13 ml of 1% acid fuchsin with 87 ml of saturated aqueous picric acid. Fourth is the acridine orange, which is a fluorescent cationic dye that is commonly used to differentiate between live and dead cells. It gives green fluorescence for DNA in live cells and red fluorescence for RNA in dead cells. It is particularly useful for cell cycle analysis and fluorescence microscopy, and it is also valuable for distinguishing cellular viability. Fifth is the acridine red 3B, which is used to demonstrate calcium salts deposits in tissues as well as to identify potential sites of phosphatase activity. It forms a red stain complex with calcium salts, making it an essential stain in the study of mineral deposits in tissue sections. Seventh is the Alcian blue, which is a water-soluble thiocyanin dye that stains acidic mucopolysaccharides and epithelial mucins blue. It is particularly valuable in connective tissues and epithelial studies, and is often combined with PAS or the periodic acid shift stain, which stains neutral mucins red. The combination of these two stains helps distinguish various components of the extracellular matrix. 8 is the alizarin red S that is used to stain calcium deposits, forming an orange-red lake at pH 4.2. It is particularly effective in detecting small amounts of calcium, such as in Michaelis-Guttman bodies, and is also used in photometric serum calcium measurement methods like in DuPont ACA analyzers. 9th is the aniline blue. Aniline blue is a cytoplasmic stain used as a counter stain in epithelial tissue section. It is a commonly employed stain for adding contrast to tissue sections, ensuring that cellular details stand out clearly. The 10th stain is the azocarmine, which is a histological stain that colors nuclei a deep red and the cytoplasm a pale red. It provides a clear contrast between nuclear and cytoplasmic components. This differential staining makes it useful for highlighting cell morphology in tissue sections where nuclear detail is critical. Next is the basic fuchsin. Basic fuchsin is a plasma stain that is used to highlight acid-fast organism, mitochondria, and smooth muscle fibers, particularly when used in combination with picric acid. It is a major constituent of stains like Fulgence reagent, Schiff's reagent, and Van Gisson solution, which are used to identify aldehydes, connective tissue, and elastic fibers. Under basic fuchsin, we have carbol fuchsin, which is used in Ziehl-Neelsen staining to detect acid-fast organism. It is prepared by dissolving 1 gram of basic fuchsin and 5 gram of phenol in absolute ethyl alcohol and water, followed by boiling and filtering. Next is the Coleman's Fulgen reagent, which stains DNA by detecting aldehyde groups after acid hydrolysis. So it is composed of 1 gram basic fuchsin, 1 gram sodium metabisulfite, 10 ml 1 normal hydrochloric acid, 200 ml distilled water. So it is prepared by boiling water, then adding fuchsin off heat, then add other components, let it stand for 24 hours, and then filter it through charcoal. Next is the Schiff's reagent, which is used to stain aldehyde in PAS and Fulgen techniques by combining basic fuchsin. So it is composed of 1 gram basic fuchsin, 1 gram sodium metabisulfite, 200 ml distilled water, and 20 ml normal hydrochloric acid. So it is boiled, cooled, sequentially add reagents, stand for 24 hours, filter through charcoal to decolorize. Next is the Mallory's fuchsin stain, which is a nuclear and cytoplasmic stain that is used as a part of trichome staining. So it is composed of 0.5 gram basic fuchsin, 50 ml of 95% ethanol, and 50 ml of distilled water. In preparing this, you need to dissolve fuchsin in alcohol with heat, then add water, cool, and then filter. Last stain under the basic fuchsin is the aldehyde fuchsin or the Gomery stain. So this stains elastic fibers and beta cells of the pancreas. So it is composed of 100 ml of 0.5% basic fuchsin and 70% ethanol, 1 ml of paraldehyde, and 1 ml of concentrated hydrochloric acid. So this should be stand for 24 hours at room temperature until deep purple, and store it in ref temperature. Another stain is the benzidine. Benzidine is used for staining hemoglobin. It is prepared in 2 solutions. Solution A that contains benzidine, sodium nitroprusside, and absolute alcohol, and solution B that contains absolute alcohol, glacial acetic acid, hydrogen peroxide, and sodium nitroprusside. So these both solutions must be freshly prepared. We also have Bismarck brown. Bismarck brown serves as a contrast stain in techniques such as Grams staining, acid-fast staining, and Papa-Nicolau methods. It is also used for staining diphtheria organism. Next is the carmine. Carmine is a chromatin stain that is commonly used in fresh smear preparation, especially effective when combined with aluminum salts to stain glycogen. Its active component, carminic acid, is responsible for its staining properties, and it is also valued in industry for detecting metal ions such as aluminum. Carmine is often used in the form of a carmine alum lake, which enhances its affinity for cellular components. The best carmine stain comes in 2 forms, stock solution and working solution. The stock solution is composed of 2 gram carmine, 1 gram potassium carbonate, 5 gram potassium chloride, 60 ml of distilled water, 20 ml of concentrated ammonia. Next is the working solution, which is composed of 2 parts stock solution, 2 parts of concentrated ammonia, and 3 parts of absolute methyl alcohol. Next is the best differentiator, which is composed of 40 ml of absolute methyl alcohol, 80 ml of absolute ethyl alcohol, and 100 ml of distilled water. Next is the Carmalum or Mayer's solution, which is a mordanted dye that acts as a basic dye, specifically used for staining acidic substances. It is composed of 0.5 gram of carminic acid, 5 gram of potassium alum, 100 ml of distilled water, 0.05 gram of salicylic acid, and 0.25 gram of sodium salicylate. Next is the Celestine Blue, which is an alternative to iron hematoxylin for nuclear staining. It is resistant to decolorization by acid dyes, and it forms a strong staining lake with iron alum, providing precise nuclear staining. It is composed of 5 gram ferric ammonium sulfate, 100 ml of distilled water, and 0.5 gram Celestine Blue, and 14 ml of glycerin. Another stain is the Congo Red, which is best known as an indicator, and it is used to stain amyloid as well as axis cylinders, elastic tissue, and myelin. It is applied as a 4% aqueous solution, and it is widely used to detect proteins deposits in tissue. Next is the crescent violet, which is commonly used in neurohistology to stain cell bodies within the neuronal cytoplasm. It highlights the acidic components of neurons, which are critical for visualizing cellular details in the brain and the spinal cord. Next is the crystal violet, which is a nuclear stain that is used for staining amyloid in frozen section and for platelet staining in blood sample. It is often combined with gentian violet, a mixture of crystal violet and metal violet. Next is ethidium bromine, which is a fluorescent DNA stain that intercalates into DNA and emits red-orange fluorescence. It is commonly used to visualize DNA in gel electrophoresis and as a marker for apoptotic cells in combination with acridine orange. Next is the GEMSA stain, which is primarily used to differentiate leukocytes in blood films. It stains erythrocytes pink and white blood cells based on the shape and size of their nuclei. It also binds to pathogens like Plasmodium and Trypanosoma, making it essential for malaria diagnosis. So it is composed of 1 gram GEMSA stain, 60 ml of glycerin, and 60 ml of absolute methyl alcohol. Next is the gold sublimate, which is a metallic impregnation stain useful for embedding tissues in gold chloride and mercury chloride. It is essential for highlighting structures that require metal-based staining methods. And we have iodine, that is one of the oldest biological stains that is traditionally used to stain starch, glycogen, amyloid, cellulose, and carotenes. It also plays a critical role in removing mercuric pigment artifacts and in enhancing dye retention during gram staining procedures. Iodine can be prepared in both aqueous and alcoholic forms, making it versatile for various histological and microbiological applications. Under iodine, we have the Gram's iodine, which acts as a mordant in gram staining. It helps to differentiate gram-positive bacteria that stains blue or purple from gram-negative bacteria which stain pink. It is also used in Gram-Wiegert method for staining elements like fibrin in tissue sections. The solution is prepared by dissolving 2 grams of potassium iodide in water first, then adding 1 gram of iodine and bringing the volume up to 300 ml with distilled water. Under iodine, we also have the Lugol's iodine, which is also called as Lugol solution. It serves as a mordant in gram staining as well, and it also used to stain glycogen, amyloid, and corpora amylosea. It is also so well known for turning black in the presence of starch, making it useful for starch detection. Additionally, it helps to highlight cell nuclei. The solution is made by dissolving 1 gram of iodine and 1 gram of potassium iodide in 100 ml of distilled water. Another is the Janus green bee, which is a vital stain used for staining mitochondria in live tissue samples. It is commonly employed in intravital staining, allowing researchers to study living cells. Next is the malachite green, which is used as a counter stain and spore stain that is effective for staining erythrocytes and ascaris eggs. It is not ideal for general microscopy, but it works well for identifying specific tissue structures. Next is the Mason's trichome, which is a 3-color stain that is used to distinguish cells from surrounding connective tissue. So the resulting colors are red for keratin and muscle fibers, blue or green for collagen and bone, light red or pink for cytoplasm, and black for nuclei. Next is methyl green, which stains chromatin green in acidic conditions, commonly used in bright field microscopy. However, it can sometimes result in false positive when applied to certain secretions like mucin. Another is the methylene blue, which is a basic nuclear stain that binds to acidic structures such as nuclei, producing a blue coloration. It is commonly used as a counterstain with AUCin Y and can serve as a substitute for Janus green bee or carmine in certain protocols. It has wide application including plasma cell visualization, bacterial differentiation, example in diphtheria diagnosis, cytological examination such as sputum analysis for cancer cells, and vital staining for nervous tissue. Under it is the polychrome methylene blue that is produced through the oxidation of methylene blue, resulting in a mixture of azures and diazoles, which enhances its staining capabilities. This stain colors nuclei blue, while other components such as cartilage, mucin, and mast cell granules appear reddish-violet. It is prepared by dissolving 1 gram of methylene blue and 1 gram of potassium carbonate in 100 ml of distilled water, then allowing the solution to oxidize at 37 degrees Celsius for several weeks. Commercial preparations are also available for this polychromed methylene blue.
Next, we have Mallory's fluoxene methylene blue stain. It is originally known as eosine methylene blue or EMB method. This technique produces a sharp nuclear stain and reveals with marked differentiation the various structures in the tissues, which should be fixed in Zenker's fluid. Next, we have methylene violet. It is a metachromatic dye formed whenever methylene blue is heated in fixed alkali or alkali carbonate, coloring nuclei of leukocytes reddish purple in the presence of methylene blue. Next, we have Nile red, also known as Nile blue oxazone. It is formed by boiling Nile blue with sulfuric acid. This produces a mix of Nile red and Nile blue. Nile red is a lipophilic stain. It will accumulate in lipid globules inside cells, staining them red. Nile red can be used with living cells, and it also fluoresces strongly when partitioned into lipids, but practically not at all in aqueous solution. Then we have oil red O. It is a dye that is more soluble in fat than in water or alcohol, hence it is used as a stain for neutral lipids. For example, when myelin is broken down in the CNS, in diseases such as multiple sclerosis, macrophages take up the lipid-rich debris and stain strongly with the dye. The oil red O stain can identify neutral lipids and fatty acids in smears and tissues. Fresh smears or cryostat section of tissue are necessary because fixatives containing alcohols or routine tissue processing with clearing will remove lipids. The ORO is a rapid and simple stain, and it can be useful in identifying fat emboli in lung tissue or clot sections of peripheral blood. Next, we have Orcine. It is an excellent stain for elastic fibers and especially recommended in dermatological studies due to its ability to demonstrate the finest and most delicate fibers in the skin. Then we have osmium tetroxide. Osmic acid or osmium tetroxide is a selective stain for unsaturated lipids and for lipoproteins such as myelin, which it stains black. Osmic acid, aside from being used as a fixative, especially for electron microscopy, may be used to stain fat, although other substances are also stained simultaneously, thereby preventing specific staining of lipids to be done. Fat, which reduces osmium tetroxide to osmium dioxide, is stained black and may be demonstrated from the tissue by using chrome osmium solutions or by the frozen section methods. Then we have periodic acid shift or PAS. It is an all-around useful stain for many things. It stains glycogen, mucin, mucoprotein, glycoprotein, basement membranes, capsules, and blood vessels, as well as fungi and intracellular carbohydrates, such as glycogen in hepatocytes. Cells that secrete mucus are also strongly stained. A pre-digestion step with amylase will remove staining for glycogen. This method depends on the selective oxidation by periodic acid of free hydroxyl groups on two adjacent hydroxyl groups converting the alcohols to aldehydes. The aldehydes are then detected by the Schiff reagent, which stains them reddish purple. Other tissue components stain according to the counterstain used. Lead hematoxylin or another basic stain is often the counterstain. Then we have phosphotungstic acid. It is a common negative stain for viruses, nerves, polysaccharides, and other biological tissue materials. This is an ideal stain for the demonstration of striated muscle fibers and mitochondria, which stain blue. A counterstain is often not used. Next, we have picric acid. It is employed as a contrast stain to acid fuchsin for the demonstration of connective tissue or Van Gieson stain, as a cytoplasmic stain in contrast to basic dyes, as a counterstain to crystal violet, as a tissue fixative, and as a decalcifying agent. Then we have Prussian blue. It is an insoluble colored salt of ferric ferrocyanide, an iron cyanide compound, normally utilized for the manufacture of paints, but may be used for microanatomical color contrast of specimens and for demonstration of the blood and lymph vessels by injection or intravital staining. Then we also have rhodamine B. It is used with osmic acid to fix and stain blood and glandular tissue. Then we have safranin or safranin O. It is a nuclear stain. It produces red nuclei and is used primarily as a counterstain. Safranin may also be used to give a yellow color to collagen. Then we also have silver nitrite. It is used in 10% aqueous solution to prepare various dilutions to be used in identification of spirochetes, reticulum, and other fiber stains. Then we have toluidine blue. It is a nuclear stain for fixed tissues used as a substitute for tanning in fresh frozen tissue sections. It is recommended for staining of nasal granules or chromophilic bodies. It is a particularly versatile dye that stains nuclei blue and can be used to differentiate different types of granules. Because it can permeate the resins that are used to embed sections for electron microscopy, it is often used as a preliminary stain to identify sections that will later be examined by electron microscopy. Then we have Van Gieson stain. It binds to collagen in the extracellular matrix, staining it pink. Often it is combined with a stain for elastic fibers, which stain black, allowing the two major elements of connective tissue to be differentiated. Then we also have Victoria blue. It is used for demonstration of neuralgia in frozen sections. Then we also have von Cossa stain. It is a silver reduction method that demonstrates phosphates and carbonates, but these are usually present along with calcium. This stain is most useful when large amounts are present, as in bone. For Wright stain, it causes blood cells to exhibit four major staining properties that allow the cells types to be distinguished. Basophilia, affinity for methylene blue. Azurophilia, affinity for the oxidation products of methylene blue called azures, which are reddish-purple. Acidophilia, affinity for eosine. And neutrophilia, affinity for a complex of dyes in the mixture, which are pale lilac. In a stained blood smear, erythrocytes bind eosine and appear orange to pink, nuclei purplish blue, basophilic granules very dark bluish purple, eosinophilic granules red to red-orange, neutrophilic granules reddish brown to lilac, platelets violet to purple, and lymphocyte cytoplasm stains pale blue. Then we have all soluble dyes or lysochromes. Lysochromes also or soluble dyes are not real dyes in the usual sense of the word because they do not have oxochrome groups. They give color to lipids simply because they are more soluble in lipid mediums of the tissues than in their medium of 70% alcohol. All soluble dyes are available in the form of Sudan Black B, Sudan 3, and Sudan 4 or Charlark R, used for the demonstration of intracellular fats which are colored black, orange, and red respectively. In order to penetrate fats, the all-soluble dyes must be dissolved in organic solvent, although the solvent vehicle, usually ethanol, isopropanol, or propylene glycol, should be sufficiently dilute to avoid extracting the lipids themselves. First, we have Sudan Black. It is a stain that colors fat droplets black and is the most sensitive of the oil-soluble dyes. It possesses two secondary amino groups per molecule, making it a slightly basic dye, which may cause nonspecific staining. Because of this molecule structure, Sudan Black has a much greater affinity for phospholipids than other lysochromes, coloring neutral lipids or triglycerides by simple dissolution of the dye. It has the added advantage of being a more sensitive coloring agent. The ability of fats to absorb Sudan Black is related to the concentration, temperature, and physical state of the fats. Maximal dye, uh, maximal dye uptake occurs when fat reaches its melting point, so that lipids that are liquid or semi-liquid at staining temperature will be stained, while those that are crystalline or solid will not be affected by the dye. Sudan Black is prepared as a 0.5% solution boiled in 70% ethanol for 10 minutes under a reflux condenser and filtered before use. It is very unstable solution and should be discarded if the usual blue-black color turns brownish-black. It usually imparts a black color on intracellular lipids and is recommended for paraffin sections, especially for tissue fixed in formal calcium with post-chroming, demonstrating lipids that are resistant to paraffin embedding. Unlike the other Sudan dyes, Sudan Black B stains phospholipids as well as neutral fats. Sudan Black B does not stain crystalline cholesterol, and free fatty acids tends to be soluble in the ethanolic dye bath. Then we have Sudan 4 or Charlotte R. It is different from Sudan Black because it has no secondary amino groups and it does not color phospholipids or define lipid droplets. It is prepared by saturating the dye in 1 part of 2% benzoic acid in 70% alcohol and 1 part of acetone, forming a very stable solution which may be used repeatedly as long as it is filtered. Addition of benzoic acid intensifies fat and prevents rapid deterioration of the solutions. It is recommended for staining triglycerides or neutral lipids, giving them a deep and intense red stain. Then we have Sudan 3. Sudan 3 was the first Sudan dye to be introduced into histochemistry. It is also fat-soluble and is good as a fat stain for central nervous system tissues, giving a less deep and lighter orange stain compared to the darker staining Sudan 4. Then finally, we have cheap solvents used for stains. First off, we have water. It should always be distilled unless otherwise stated. Then we have alcohol. Ethyl alcohol may be used in various concentrations. Methyl alcohol, if to be used, is usually absolute and is indicated, especially in the preparation of bloodstains, for which reason it should be acetone-free. Then we also have aniline water. 10 milliliter of aniline is added to every 1/2 to 1 liter of hot distilled water, shaken, cooled, and filtered. Then lastly, we have phenol. It is used in aqueous solution of 0.5 to 5%.